Well, good evening, everybody. This is AP Physics C, Electricity and Magnetism, and my name is Kristen Gonzalez-Vega. I am coming to you from Frisco, Texas, where I teach at Reedy High School. And tonight, as always, I have with me Roger.
Hello, everybody. My name's Roger Siegel, and I live here in Sarasota, Florida, and I teach at Pine View School, and we're glad you joined us.
Okay, and we are getting closer and closer every day, guys, to the big day and being done. So we are reviewing today electric potential and electric potential energy in uniform electric fields. We started talking about point charges yesterday, so we're just kind of continuing on from that. If you didn't catch it, it might be good to go back and look at that even after tonight. You can still watch this tonight. You'll be perfectly fine, but go back and take a look at that. Our objectives today are to be able to describe the relative magnitude and direction of an electrostatic field given a diagram of equipotential lines. We want to be able to describe characteristics of a set of equipotential lines given in a diagram of an electric field, right? So we need to be able to kind of translate between one and the other. If you're given the electric field, can you create or describe the equipotential or the potential lines, and vice versa? And then lastly, use the general relationship between electric field and electric potential to calculate the relationships between the magnitude of the electric field or the potential difference as a function of position. Okay. So kind of a review from last night. What is electric potential? It is not something we can measure, but it's something we can kind of qualitatively say or quantitatively say is the amount of energy per charge. So that is something we can calculate. So we don't have a electric potential meter. Now we can find the electric potential difference between two places. So that is something that generally we find a little bit more meaningful to talk about, is what is the electric potential difference between 2 points or 2 regions, parallel plates or terminals of a battery. And that is something you can measure. We can relate the electric field to the electric potential, and we're going to derive that right now. So what is the relationship between the electric field and the electric potential? Well, we're going to start with our old relationship that we go back to all the time with forces and energy, potential energies. And that is that relationship that the force is equal to the negative derivative of the potential energy with respect to position. So if we start there, we're going to get a relationship for the electric field and the electric potential. So if we know that the force is equal to the negative derivative, why is it that negative derivative, right? That's one of the big questions in physics. We see it a lot in mechanics, right? Any of those forces that are related with a potential energy, and we mentioned this last night, are conservative forces, right? Spring potential energy, US, gravitational potential energy, UG, and now electrostatic potential energy, electric potential energy. Those are all conservative forces. They're associated with a potential energy. They're also do not depend on the path, right? Independent of the path taken, the amount of work done. So it's always the negative because the force is positive and doing positive work when you are losing potential energy, and doing negative work when you are gaining potential energy. Okay. So I can turn this force, though, because if this is the electrostatic force, that's the negative derivative of potential energy, we'll say it's the electric potential energy then over dx. Well, how can I find that electrostatic force if we're in a uniform electric field? So if we're in a uniform electric field, how could I find what the force on a charge is? Well, that's Q times E. So that equals our negative derivative of the potential energy. Okay, well, if I want the relationship for the field, well, I'm going to divide out by the charge to get rid of the charge. So really, I get the electric field is equal to the negative derivative of the energy over dx times q. Well, we said just a second ago and last night, I talked about it a lot. What is the relationship between the electric potential energy per charge? Well, that is that electric potential. So then we can say that E is equal to the negative derivative of the potential with respect to distance. If we were to see that in a graph, what would be significant about that? Well, we call that derivative is equal to the what on a graph? The slope. So if we have the potential versus position graph, no matter what shape it is, that slope is equal to the electric field. The slope of the potential is the electric field. That's if it's changing, right? We can use that dV over dx. But if it's not changing, or if it's uniform, or just a nice straight slope, we could also say this is delta V over delta X. So that one we use a lot too. Okay, so just kind of a way that we can look at that relationship. So if we kind of put a little list of important equations here off to the side, well, we know that the potential is the amount of electric potential energy per charge. We know now that the electric field is the change in potential over the change in distance. We know force is Q times E. We know that work is the negative change in energy. And we may add to that, right? But that's just some things that we can be thinking of, are those relationships, because we have a lot of kind of back and forth and ins and outs and relationships that we're going to substitute into. So I'm going to show you now how we can also graph this. So one way we can graph and talk about potential is we can look at the potential as a function of position, right? So if we have a charge on an axis, x-axis here, and I just want to know, as a function of the position, what is the potential? Right? And we know that when we looked at point charges from a couple of nights ago, or maybe that was even just last night, it's all blending together, right? That the potential of point charges is equal to kq over r. So if we look at that relationship, it's a 1 over r relationship, right? So we could graph that potential as a function of the position. We could also look at what those potential equipotential lines look like around a charge, because if I am the same distance around my one charge, well, what's going to be true about the potential everywhere on that one spot? It should be the same. So we can plot these equipotential lines where they have the same potential, right? Equipotential means equal potential. So I have a PhET simulation here that I have pulled up to show you. I'm going to switch my shares here. And I have already plotted some equipotential lines here. So I've put two positive charges on here. And what I've done on the left side here, on that left positive charge, if I show you my little potential meter, right, which we don't really have, but I kind of graphed it and plotted every 10 volts. So if you notice, as we go out every 10 volts, what happens to, and I couldn't really go further out here because, again, we have that other charge interacting. But if you notice those lines, they're getting further and further apart. And so another way we can kind of give another comparison to are those topographic maps, right? If we kind of imagined this as a topographic map, we know that as elevation goes up, we kind of draw those lines closer and closer together. So we can also imagine that potential as these nice peaks, which kind of sometimes helps think about what objects or charges are going to do when they're in this potential, right? If I'm on the top of a hill, a marble wants to roll down. Well, if I have a charge at the top of our equipotential hill, it wants to roll down too. And so we can draw these lines, and the main thing you want to remember that everywhere on these lines, that potential is the same. So we're also going to look at how the electric field looks with regard to these potential lines. So if I add in our electric field, I want you to take a minute, and what do you notice? What do you notice about these electric field lines? If you look at one of these field lines with respect to the equipotential lines, what do you notice? Well, they're perpendicular at every single point here on these potential lines. Okay, so that's one thing that is always true. Our equipotential lines and our electric field lines are always perpendicular. And we know that our electric field lines always point away towards lower potential. So if we look closer here, if I get my meter out here, and we can see we've got 31.07 volts here. I've got 19.66 here, right? That field line is pointing towards the lower potential. So those are the couple of things I wanted to show you on that. So let's go back here. And those are kind of our takeaways, right? On one contour line, the electric potential is the same everywhere. And the electric field vector is going to point perpendicular to that electric potential and points towards the lower potential. So let's kind of also look at here if we have a parallel plate. If I have this parallel plate and it has an electric field in between, uniform electric field, and I know the distance between my two plates, what kinds of things could I find out about this? Well, one thing I could ask you is what charge does the left side of the plate have? And you would all tell me the left side has a positive charge. Therefore, the right side has a negative charge, right? Because the electric field lines are going to point from positive towards negative because they're pointing away from the higher potential towards the lower potential. Okay, so the next thing we want to look at here is which way would a proton have to move in order for the work to be done by the electric field to be positive, right? So if I want the work
Go
done
ahead
by
and
the
show
electric...
us your screen, please.
Oh, sorry, I thought I clicked share. There it is. Thank you, Roger. So if I have a positive charge here, let's just place it right in the center. Which way would this positive charge have to move in order for the work done by the electric field to be positive? Okay, and vice versa, I also want you to think about which way would an electron have to move in order for the work done by the electric field to be positive. Okay, so those are the two questions I have for you first. Which way would each of those have to move in order for the work to be done to be positive? I'm going to make a little chart here. Okay, so the first thing I want you to think about is which way would the force be acting on each of these charges? So if we have our positive charge, which way would the electrostatic force be on this positive charge? Well, the positive charge wants to be forced towards the negative side. The electrostatic force on a positive charge is always in the same direction as the electric field, and in the opposite direction for the negative charge. So I'm going to say, well, for the positive charge, if we're calling to the right positive, then this has a positive force acting on it. And the negative charge has a negative force acting on it. Okay, well, how do we get work? Work is force times that parallel displacement, or the parallel component, right? This is already parallel. We don't have to worry about that dot product. So I want to look at, well, if I want to have positive work on the positive charge, the force is already positive. So which way does the distance have to be? Do we want a positive displacement or a negative displacement? Well, to get positive work, I want a positive displacement, which means it has to be moving to the right. Okay, let's look at the negative charge. The negative charge has a negative force acting on it. So if I still want positive work, what do we have to do with the distance? Well, the displacement has to be in that negative direction to still give us a positive work. So the negative charge has to be moving to the left. Okay, and then the opposite, obviously, for negative work. My force is still positive. That I can't change unless I change the polarity of the plates, right? So if the force is still positive in this direction, to get negative work, I have to have a negative displacement. And same thing for the negative charge. If the force is still negative, if I want a negative work, I want positive displacement. So it is moving to the right. So in general, for the work to be done by the electric field to be positive, the charges have to move the way they kind of want to move, right? If a positive charge wants to move away from the positive side towards the negative side, then the electric field is doing positive work when the charge is doing what it wants to do. The negative charge wants to move towards that positive side. So positive work is done when it's doing what it wants to do. Okay, and when we have a change in energy, well, we know the change in energy, work is equal to the negative change in energy, or change in energy is equal to the negative work. So a lot of times this might be sometimes easier to think about with like the gravity and gravitational fields, right? The gravitational force is doing negative work when we are gaining potential energy, when you're lifting a box up. So kind of the same thing here. If I'm moving the charge and the charge is gaining potential energy, that means that's when the field is doing negative work. Okay, so our change in energy, when it's going to the right, so let's link this up. When does it have a positive gain in potential energy? Well, that's when our work is negative, or when it's going to the left. And for our negative charge, that would be when it's going to the right. Okay, so those are kind of some main things I wanted to point out with you, because sometimes looking at these fields and the charges and the work and the energy can get really confusing. But if you kind of put the analogy with the gravitational fields, it's really easy to remember. If you lift a box up, you're doing positive work, but gravity is doing negative work on it. And anytime you're lifting it up, it's gaining potential energy. Okay, so I'm going to toss it back to Roger. He's going to do some practice problems with you.
Okay. Thanks a lot, Kristen. And hi again, everybody. So yeah, we're going to keep learning about potential. So let's go ahead and let me share my screen with you guys, and we can look at some problems that we're going to do. Okay. So of course, this is what we call an equipotential diagram. And so again, as Kristen mentioned this, I'm going to keep coming back to this analogy. In Florida, we don't have a lot of terrain because it's flat everywhere, but I always manage to get to some place that's hilly, and I love to hike around. And this tells me, if this were a not a electrical potential diagram, if it were a gravitational potential diagram, it would tell me the contour of the land. It would tell me where the land is, where it's steep and where it's gradual. And so if we think about that, if we think about these potential surfaces as, if we think of as height as a potential metaphor, not, 100% ironclad, the best metaphor, but a really good one, I think it's going to help us a lot. So let's look at this equipotential surface. So we've got 3 point charges, and they create this surface, and that really doesn't become a big part of it, but just know that there are point charges that create this surface, and here are contours. Now it says draw an arrow at each of the labeled points indicating the direction of the electric field. So you can see we have all these points. Now there's a couple things that Kristen told us about electric fields and equipotential surfaces. So let's go ahead and take a look at that and see what that is. So if we come here, we can just get this thing to fit. That's perfect. Okay, good. And so so here's our point A, and every place where we have an equipotential surface, the electric field is perpendicular to that equipotential surface. So there's A, I'm going to draw a perpendicular, B, a perpendicular, C, a perpendicular, D, a perpendicular, E, a perpendicular. So every place, the electric field everywhere is always perpendicular to the equipotential line. Now the question then is, okay, we know that the electric field is a vector. I've got the direction in this way, but is it down, where do I put the arrow? Well, again, the electric field always points towards a lower potential. So you can see here up in the upper left-hand corner, we have our -60, and down here we have our +80. So clearly the lower potential is in this direction. That's my lower potential. So I'm going to go ahead and say that my electric fields are all in this direction towards these lower potentials. See, from 30 to 20 in that direction, or from 0 to -10. So this is my direction. So that's my direction there. All right, great. Let's go ahead and look at the next piece. It says, draw the electric field line that goes through point C. Let's see. Well, I thought we did that, but the electric field line, I'm sorry. So the electric field line goes through point C. Well, we know that it's going to be perpendicular, parallel here, but look, it's also perpendicular here. It's also got to be perpendicular here and perpendicular here and perpendicular here. And then it's probably going to be like this. Now, please do not confuse this line with a path that the charge would take. Okay, the charge is not going to take this path. However, this tells me in which direction it will be accelerating. Again, don't confound acceleration and velocity, because since this is the direction of the electric field, this is the direction of the force, because F vector is equal to Q E vector. All right, so that would be the electric field line through point C. At which point is the electric field the strongest? Now, this is where we go back to our analogy of a terrain map or a topo map. If you recall, if you've ever seen a topo map, you can imagine what it's telling me. It's telling me equal areas. So wherever there's a cliff where the terrain is very steep, I have these very close together. And so in the same way with potential. Remember, potential is also the negative. I'm sorry, let me back that out. Not true. All right. The electric field, sorry, is the negative derivative of potential. So what does that mean? Well, that tells us that wherever this is closest together, wherever these lines are closest together, that's where we have the strongest electric field, because the electric field is essentially the slope of this terrain, the magnitude of it. So if I look at A, B, C, D, and E, well, clearly A is where we have the lines closest together. So we'll say close together lines. So we remember that, equipotential lines. And it's the weakest where they're furthest apart. So if you look over here at B, C, not E, but maybe D, that looks like a really big distance to the other line. So I'm going to go ahead and call it on D, although it is a close one. All right, let's go. Suppose the distance between D and E is 6 meters. Estimate the electric field strength. Now look, electric field strength is, in a calculus sense, negative, and we'll put it over here again, is equal to negative dV dx. And that's, in one direction. We'll do it one direction at a time. Well, that if we approximate that, we can say that the electric field approximates to the change in voltage. That's not velocity, that's voltage, over the change in x. So we see from point D to point E, look at this, we're going from 0 volts to point E at negative 30 volts. So that means we have negative 30, okay, minus 0, and the change in distance here is 6 meters. And so that is, by the way, volts. And so what we get is 5 volts per meter. And remember that the electric field has 2 different units. One unit for the electric field is newtons per coulomb. The other one is volts per meter. All right, and then we got 2 more on this page and we'll move on. This is a 5 kilogram object with a charge of 0.1 coulombs is released from rest at point A. It follows a path to point E. How fast is it moving when it reaches point E? Now, it's released from rest. Now, again, do not confound this line with the actual path. This is the direction of acceleration, not necessarily the path. But let's imagine that it is released here and it follows some line and it gets over here to point E. And so let me try that again. And so it'll go here and it gets to point E. And so the question is, what is its speed? Well, remember, again, this is our analogy that works well for us. It's rolling downhill. Positive charges roll downhill. And so that means that its change in kinetic energy shows up because there is a change in potential energy. Now, let's go ahead and take a look at that. Try that a little bit, and I'll do some work here. A lot of algebra coming our way, so let's give it a try. All right, so we have 1/2 mv squared is equal to delta U, and that's going to be Q delta V. Now, let me just stop for a minute. This V is voltage. This V is velocity or speed. They're not the same, obviously. So be careful. That's why I put the little line under this V. All right. So that means, ladies and gentlemen, if we do a little algebra, we get V squared is equal to 2Q delta V over M. Or V is equal to the square root of 2Q delta V over M. So we can go ahead and fill that out, and we have the square root of 2. The charge is 0.1 coulombs. Okay. The voltage, the change in voltage, and let me put that, I forgot, I told you I was going to write that. That's the voltage, the big V, and I put the little line to tell me that's big V. And the change in voltage, so we need to go back to our picture here and take a look at it and see what we have. And so here we can see if we go from point A to point E, we're going from 70 volts to negative 30 volts. So the change in potential is going to be negative 100 volts. All right. Now I'm going to put a positive 100 because we're under the square root, and I wouldn't want to do anything to mess that up. We'll talk about why that's negative. And our mass is 5 kilograms. And so when we do this work, what we get is that this equals to 2 meters per second. But I want you to notice that what this is this is our classic conservation of energy problem, except instead of getting its kinetic energy from rolling downhill from a change in gravitational height, we get a change in potential, electrical potential. All right, now same object placed at point B, an external force acts on the charge and causes it first to move to point B, then to point C. How much work is done by this force? All right, so let's take a look now. If I start over here, and again, I'm going to move from point, let's start at point B, and it is moved by an external force to point D, and then it's moved to point C. So that is how much work is done by the force. Well, the change in energy is equal to Q delta V. But look, delta V, I started at B, I went to D, and then I came back to C. That means that the change in energy is 0, and the work done is 0 as well. All right, let's go down and do real quick a couple more. We've got 2 charged cylinders running parallel in and out of the plane as shown. The page is shown. And the question is, you can see here's our equipotential lines. And so is the conductor on the left positively or negatively charged? Well, since it's making a positive, causing a positive potential like this, we say that it's positively charged, and as well as the conductor on the right. A particle is brought from point D to point B. Through what potential difference does the particle pass? Well, the particle goes from D to B, which means it goes from 200 volts to 75 volts. And so that's going to be negative 125 volts. It loses 125 volts of potential. That means that it's going to gain kinetic energy. It's going to be moving faster because it lost potential. All right, and then finally, a particle that carries a charge of 1 coulomb moves from point F to point G. How much net work is done by the force of the field, by the electrical force? Well, the work done by the force is going to be, again, Q delta V, and so that's going to be 1 coulomb, and the change in voltage from F to G is 100 volts. And so remember, a volt is a joules per coulomb, so that's going to be 100 joules of energy that will be given to that object. And then finally, down here, same picture, we're asking the same question. What direction is the electric field at point B. So let's look at B. Well, we know the direction is going to be perpendicular to B. Is it to the left or to the right? Well, remember, the electric field always points in the direction of decreasing potential. And so that's to the left or 180 degrees. If a proton is placed at point F, what direction will it feel a force? Well, a proton is positive, and the electric field is going to be perpendicular and pointing to the lower potential. And so the direction it will feel a force is in the direction of 135. And then if an electron is placed at point E, what direction will it feel a force? Well, the electric field at point E is in this direction. But ladies and gentlemen, it is an electron. And so an electron is negative, it will feel a force in that direction or negative 90 degrees. So I hope that helps you to understand a little bit more about equipotentials and how they tell us what's going to happen to a particle and how its energy is going to change. So again, just keep trying to picture those terrains, and that should help a lot. Kristen, I know you're going to take us home. What you got?
I am super impressed at how efficiently you got through those, Roger. We have one, maybe 1.5 questions to look at. The first one here is from, I think, 2016, if you want to go back and look at it later. It is an electric field diagram above, right? So we've been looking at some equipotential lines and equipotential mapping. Now let's turn and look at, now we have the electric field lines. So points A, B, and C are all located at y equals 0.06, right? So all on that same kind of horizontal level there. And we want to know at which of these 3 points the magnitude of the electric field is the greatest, and justify your answer. At which of these 3 points is the electric potential the greatest, and justify your answer. And then B, an electron is released at rest from point B. Qualitatively describe the electron's motion in terms of direction, speed, and acceleration, and calculate the electron speed after it has moved through a potential difference of 10. So I'm going to give you just a couple of minutes here. I want you to, first of all, I want you to mark up and write some different things on that electric field line diagram. What kinds of things stick in your head that maybe you would do, or you could label or draw on that mapping. Okay, and then I want you to answer A and B for me. And I'm gonna give you a couple of minutes to think about what you would say, jot down some stuff on a piece of paper, and then we'll discuss. And you might need some more time, especially on part BII, but we'll go ahead and go over it. If you need to stop and pause at any time, you can. So when I'm looking at this electric field mapping, the first thing I'm going to look at is I want to look at which way those arrows are pointing. I want to look at where those lines are close together, where those lines are spread apart, because those are going to tell us things, right? Where we have these lines really close together, what does that mean when those electric field lines are close together? Well, that tells me that there is a bigger magnitude of that electric field. And when they're more spaced apart, I know I have a smaller magnitude of electric field. Okay, which way do those lines point? Well, electric field lines are always pointing from that higher potential to lower potential. Right, so I'm kind of thinking these things through when I'm looking at these diagrams. If I were to draw the potential, the equipotential lines, well, what can we do? We know that they're always perpendicular to the electric field at every point. So if I wanted to, I could draw some of those lines on there. Okay, we'll save that, but let's look first at A. So which of these points, A, B, or C, are going to have the greatest magnitude of electric field? Where is the magnitude of the electric field the greatest, right? Well, if we were already kind of looking through those diagrams and thinking about it, we know that it's going to be greatest at C. What would we write for our justification? Right, we want to use those good physics terms in our justification, right? So at C, it's the greatest. And how do we know it's the greatest? Well, it's because the electric field lines are closest together. Okay, what about where the electric potential is the greatest? Well, again, if we were looking and we were analyzing that before we even read the question, oh, I'm kind of frozen here, aren't I? I'm going to stop and reshare. So if we're looking at where that potential is the greatest, we're looking for, yeah, I'm going to pull it right back up. I'm just chatting away while I get it working again. So what are we looking for on that electric field mapping? Well, we're looking for where we know that the electric field is pointing, because we know the electric field is going to point from that higher to lower potential. So which side is closest to that higher potential side that we identified? That would be point A. So A would have the greatest potential, since the electric field points away from the higher potential towards lower potential. So we want that leftward most point. Okay, let's look back at this and say, what's going to happen to an electron if we placed it at B? So let me change colors here. Okay, so if we place an electron at B, what is going to happen to it? And we want to describe over a long period of time what's going to happen to it. So first thing we want to know is, if I want to be able to describe this in terms of the acceleration, the direction, and the speed, well, if I'm going to describe the acceleration, which really relates to the speed and the direction, everything, it depends on which way that force is. So we want to think about which way is the force going to be on that electron. Remember, electrons feel forces in the opposite direction of the electric field. And so that would be to the left. So we know that the force is going to be to the left. So if the force is to the left, what does that tell us about the acceleration? Well, if we know F equals ma, if the force is to the left, then the acceleration is going to be to the left. So we know it's going to accelerate to the left, but what does the magnitude of that force and therefore the magnitude of the acceleration relate to? Frozen again. Sorry, guys. Well, force is equal to Q times E. I'm going to try this one more time. If it doesn't work, we're just going to go back to the PowerPoint. Okay, so we know the force is related to Q times E. So we can say, well, is this field the same? Well, no, because as this goes towards the left, what do you notice about the distance between those field lines? It's getting bigger and bigger. So if the distance between those field lines is getting bigger, we know the magnitude of the electric field is getting smaller. So if the magnitude of the electric field is going down, then we know the acceleration has to be going down. Okay, but it's still speeding up, right? So it's speeding up to the left, but the acceleration is going to be decreasing. So it's still speeding up, but it's kind of like free fall, right? When there is air resistance, we start with that big acceleration downwards because our drag force up is really small. Remember, drag relates to the velocity. And as you are falling and that drag force gets bigger and bigger, you're still speeding up as you go down, but the rate at which you're speeding up is getting smaller, right? This is the exact same thing. You're going to be speeding up to the left, but the rate at which you're speeding up is going to be decreasing. Okay. And then how would we calculate? So I just want you to describe it. How would you calculate the speed of that electron, after it has moved through a potential difference of 10 volts? So I'm going to switch over while you're going to describe that. I'm going to switch back over because this is going to keep freezing up on me. Okay, so we're on this part right here, B, calculate the electron speed after it has moved through that potential difference. So how are we going to get the speed? Well, when it's at that original location, we're going to relate, just like Roger did on that last problem, that our change, if our potential energy is changing, that electric potential energy is changing because its location in this electric field is changing, that's going to turn into our kinetic energy. So whatever potential energy I'm losing by changing through that potential difference of 10 volts is going to be gained into kinetic energy. Okay, so we could set, how do we get that electric potential energy? Well, we know that it's equal to, if V is equal to U over E, then our V is equal to Q times V. But if we want delta U, then really I want delta V. And that's going to be equal to our 1/2 mv squared. And then we could find out what that velocity is using that potential difference of 10 volts. Okay, so I want you to look at then points B and C, and if they are separated by a potential difference of 20 volts, estimate the magnitude of the electric field midway between them and state any assumptions that you have to make to do that. So I want to know if the separation of these two is 10 volts, then how could we find what the magnitude of the field is at a region at a point midway between them? What's that relationship between the electric field and the electric potential? The electric field, remember, is equal to the slope or the derivative of that potential, negative. So since we're talking big here, let's use that negative delta V over delta X. Right, so I'm using that B to C, that's what I know the potential difference of. So if they're just giving us that it's separated by a potential difference of 20 volts, then we can say that 20 volts, well, we've got to estimate what that distance is between B and C. Well, B is at 0.08 meters, oops, sorry. And C is at 0.09, so they're separated by a distance of 0.01 meters, which would give us then 20 over 0.01. We move that decimal 2 places and we get 2,000 volts per meter. Okay, what was an assumption that I had to make in that? Always got to be thinking about those assumptions, right? What are the things that we are assuming? I'm assuming that that is a uniform field in that region, right? That it's a constant electric field between B and C, that it's not changing if I'm using that whole change between them. Okay, and then on the diagram, draw an equipotential line that passes through D and intersects at least 3 electric field lines. What's the key? We have to stay perpendicular to that electric field at every point. So if we wanted to go through D, if we want it to go through D and we want it to be perpendicular everywhere, going through at least 3, we can go through more than 3, can't we? Then I would be drawing my equipotential line like that. Okay, we are out of time. I'm going to put up one just for you to think about. Just the first question I have for you, we're not really going to look at these. What I want to know is, looking at these two charges and looking at these equipotential lines, I want you to tell me for tomorrow, which of these charges, well, we know that the magnitude of charge 2 is 2 nanocoulombs, right? So looking at these equipotential lines, I want to know, is Q1, the magnitude of Q1, bigger than, less than, or equal to the magnitude of Q2? Okay, so that's our $1 million question for tomorrow when we come back. Is Q1 bigger than, less than, or equal to magnitude-wise to Q2? Okay, that is all we have then. We will talk about that tomorrow. So you should be able to relate those electric fields and electric potential, the graphs of each. How can you go back and forth from one to the other? And what was that relationship between the field and potential? Tomorrow, we're going to do electric potential of our fun other distributions of charge, meaning that ring, that arc, and that line of charge. And then Friday, we are going to finish out potential with concentric conductors. So, Roger, what have you got for the rest of tonight?
What have I got? Just a big thanks for tuning in and a big good luck. And we hope these are helping.
All right, have a great night.